So good morning to everyone, or also good afternoon for some of you, or also good night for some of you coming from Canada. So as said Amalia, we shall spend all the day together. So my name is Pottier. I'm from Rennes in France, in Brittany. So if you don't know where is located Brittany, here is a map of the France, and in the red square. This is my home city, Rennes, in Brittany, and to illustrate this lecture, I shall start with some beautiful parametric SAR images of my area, which were measured with HALOS 1 some years ago, the Japanese space-bound sensor with Datasets 2, the Canadian space-bound sensor, HALOS 2, Japanese, and Sentinel-1. And recently, we got the image of our area with the Chinese system, Gaofen 3, GF3, which is a very, very nice fully parametric SAR system. And we shall come back to this sensor later on. And to conclude this short introduction, Brittany is also very known by these nice people. I'm not even on this picture. Okay, so we shall spend all the day together. And I shall present to you the different covered topics. I shall try to explain to you, and the objective of this lecture is to provide to you the minimum but the necessary amount of knowledge required to understand the scientific works on radar parametry, and which will cover different topics. Today we shall focus on POLSAR, which means parametric SAR image. So it means that we shall process only one image, fully parametric SAR image, and we shall see what we can do with each pixel, which kind of signal processing, which kind of data processing we can apply on each pixel to extract different physical parameters or geophysical parameters. Then POLSAR will be also covered tomorrow with Armando. So today and tomorrow we shall focus on POLSAR. On Thursday, we shall move to one image more to create what we call POLINSAR, parametric interferometric SAR, with Professor Irena Hanczek. And so in such a case, we shall see how we can, or how it is possible to reconstruct vegetation, height of the trees, biomass information. And to conclude this week, on Friday, with Stefano Tebaldini and Laurent Ferrofamil, we shall move to another dimension using different tracks, different SAR images. We shall use, if I remember, nine different SAR images, parametric SAR images, and to cover this very important new topic, parametry plus tomography SAR. And you can see on this slide different illustration when it is applied on ice monitoring, on snow monitoring, and on Friday we shall focus on forested areas. There exists also another topic which is becoming more and more important, is what I call the pole time SAR, or parametric time series SAR. And this is becoming very important because due to the revisit time of our new parametric sensors, which is reducing. So for example, you can see on this slide with HALOS 2, we have a revisit time of 14 days. It's quite okay. And biomass, it will be 4 days. Datasets 2 today, it is 24 days. POLSAR 1, 25 days, Sentinel-1, 6 days, etc., etc. So it's very important because now you can extend all what we have done with parametry to make an analysis of a temporal evolution. So you have an illustration here concerning fluid monitoring. You can see the extension of the water during time evolution. Or here, concerning subsidence monitoring with permanent scatterer or coherent scatterers. So this is very important. This is a new topic. which is becoming more and more important, but we shall not present some results using on this new topic. So the different topics I'm trying to present to you are the following. So the first chapter, if we can call that chapter, will be about electromagnetic wave polarization. And this part is a historical part, but it's becoming more and more important due to the dual pole system. And we shall see later on what means the dual pole system. And we are coming back with this new sensor to the previous theory of polarimetry about the wave polarization. So we shall see the wave propagation, the wave polarization, the description of the polarization using the Jones vector. Then we shall move to another topic, which is scattering polarimetry. So this is all the tools we can use when we want to process a fully polarimetric SAR image. Fully polarimetric, not dual pole, but fully polarimetric. So I shall present what is a scattering program, what are the different polarimetric descriptors we can use. Something which is very important concerns the elliptical basis transformation. And we shall focus on one point which is very important, which concerns the target decomposition theory, because this is becoming something more and more important quite every month. We have some scientists who propose a new decomposition theorem. So this is very important. This is very nice. And to conclude, if we have time, we shall focus on some example of segmentation using polarimetry information. And tomorrow morning, we shall be together again, the first part of the morning before the coffee break. And I shall focus on this part, which is about wave polarimetry, because 2 years ago, a lot of students asked me different questions about polarimetry using Sentinel-1 data. And I have seen that there was a total confusion between fully polarimetric processing and dual pole processing. And this is something which is very important. So I would like to focus on this point to provide to you the information to be careful when you want to process dual pole. It is not at all the same thing that when we process a full pole. So I shall focus on this part tomorrow morning. Okay, so this is the program. And to illustrate these parts, so we shall make some practicals together using Pulsar Pro and the new version, which is Pulsar Pro Bio, which concerns the biomass edition. I put online last week the new release, the version 6.0.3, and we shall use the virtual machine to practice with some examples and using this software, this toolbox. Okay, so if you have no questions concerning this introduction, we can start with the general introduction. You can chat. I put the chat window in parallel so I can see at the same time if you have questions, no problem. So we are going to start with a general introduction. And in this general introduction, I shall make a recall about the history of polarimetry. Then I shall present not airborne, but more space-borne polarimetric SAR sensors. The past ones, the current ones, and the future ones. Then some words about the software toolbox, and some information about learning or training. Okay, so if we come back to the definition of radar polarimetry, so radar, you know what it means. Polarimetry, polar means polarization, metry means measure. So radar polarimetry is a science. Yes, it's science to acquire, to process, and to analyze the polarization state of an electromagnetic field. And so, for sure, as you can see on this slide, you have two components: the green one, the blue one. So it means that somewhere you are going to deal with a full vector nature of a wave. And what is very important is that since a long time, we have seen that the interaction of electromagnetic wave with an environment, so it can be an artificial environment, it can be a man-made environment, it can be a natural environment. So due to this interaction, you have a change of the polarization of the wave. So the idea was the following: if I am able to measure this change of polarization, maybe I shall be able to reconstruct some information. And we have shown that it's possible for example, for man-made target, it's possible to reconstruct the geometrical structure of the target, the reflectivity of the target, the shape of the target, and most important, the orientation of the target. And for natural environment, today we have a lot of studies which show that it's possible to reconstruct the geophysical properties of this natural environment, like roughness, like soil moisture, like biomass, etc. So this is why this change of polarization means something. Okay, so the idea is to measure this change of polarization. And along the time, we have seen that polarimetry becoming more and more important in all these applications. So I shall not go into the details. You have a list here. But on the main topics like forest and vegetation, like agriculture, like snow and ice, and now like urban areas, you have more and more application using polarimetry. Because by definition, you are going to increase the dimension of your information. Because, as I said previously, you are going to deal with the full vector representation of the wave. So by definition, you will get more information. So by definition, you will improve the reconstruction of all these parameters. So this is why it's very useful to have fully parametric SAR sensors, airborne or spaceborne, whatever, but fully parametric sensors. Okay, so now let's start with a bit of history about radar polarimetry. So everything started, in fact, a long time ago. As you can see, it was around 1000. But it was used by the Vikings to discover a stone, a crystal of calcite, which is called today the sunstone. And they were using this stone, and with a phenomenon of B refulgence, they were able to find the direction of the sun. Like that, they can navigate on the North Pole, where the weather is always covered. But in fact, they were using the polarization of the sun. They were using the polarization of the light. And so like that, they were able to find the right direction. So in fact, they are doing for the first time some polarimetric signal processing. Okay. Some physicists, some years ago, just succeed to demonstrate the theory of this crystal. And you can find this stone only in Denmark. It's very strange, but it's very interesting that this crystal of calcite is very specific. Then came, some years later, the first PhD thesis of this guy, which is named Bartholinus. And it's very interesting because you can find, I found it, you can find his PhD thesis on the internet. So it's written in Latin. It's impossible for me to read the Latin, but anyway, it's very funny because you can see some painting, some drawing of the first experiences he tried to understand the different phenomena of the polarization of the light. And the most important was about the double reflection of the light on the calcite. So he was the first who experimented polarimetry. Then came different scientists, you heard about them. Huygens, who discovered the nature of the wave, of the light, and gave an explanation of the double reflection. Then Newton about the model of the light, which is a corpuscular model. Then Malus, the French guy, we discovered, in fact, the polarization. Interestingly, the definition of the polarization of the light. In fact, it was not a definition of the material, but it was directly the definition of the polarization of the wave. Then we have a great collection of scientists, of physicists, who were working on optical. And it was the beginning. They were working on the nature of the light wave. So like a Brewster, you know the diffraction due to the Brewster angle, the Fresnel coefficient, the Faraday rotation. We heard about the Faraday rotation yesterday when we had the presentation of biomass. It will be something very interesting when the biomass system will be launched, to be able to study really the Faraday rotation during the ionospheric propagation. Then we have Stokes, who describe the vector of the light using only intensity information, no phase, but only intensity. Then we have Maxwell, which is more or less our god, who discovered the theory of electromagnetic theory of light. Then we have Helmholtz, Rennes, Kirchhoff, etc. And then we have a second list of physicists working on optics, Hertz, Duc, Schulfeld, Poincaré, and Lee. These two guys are very important because, as I said during my introduction, today, due to the dual pole system, we are coming back to the theory which were described by Poincaré and Lee, and we are working more and more on the group of Lee. It is a mathematical group of different matrices, and also the Poincaré representation of the polarization. So we are coming back to this theory. Then we have Lorentz, Marconi, Wiener, etc., etc. And in fact, radar polarimetry was born in the 50s. Was born in the 50s by this professor, Keno, from America, University of Chicago. So he has the idea to apply all the theory which was derived previously in optics to the radar concept. And he said, in fact, what is the difference between an optical wave and an electromagnetic wave? It is exactly the same thing, except the frequency, but from a physical point of view, it is exactly the same thing. So maybe I can apply exactly the same theory, and this is what he did. So he developed the first radar system. He developed the first polarimetric radar system, and he made the first measurement. So in fact, we can say that today, radar polarimetry was born in the 50s. And we had three guys, God and the two sons. This is what we call the radar polarimetric triptych. So Keno was the father. Heinen developed the concept of the understanding of the polarimetric information. He did a PhD about the phenomenological analysis of radar targets. So he was not able to derive all the equations, but he was able to do different experiments. So this is why he called his PhD phenomenological aspect. And then we had Professor Borner, who passed away recently, who also developed a lot of works and make a lot of contacts worldwide about the scientists working in polarimetry. So I was very lucky because I had the chance to work with Heinen and to work with Borner. Heinen was in my PhD defense, and Borner was in my habilitation defense. So this is a radar polarimetric triptych. And then we have a great collection of scientists working in polarimetry. I'm not going to go into the details, but for example, you will see Irena, you have seen Thuy, Le Temps yesterday, you will see Irena tomorrow, you will see Laurent on Friday, etc. And so we are still working. I like this slide because usually when we give this parametric training, the following week we have the SAR workshop. And very interesting because it is a way to introduce all the scientists you can meet the next week during the SAR workshop. So here it will not be the case, but imagine usually it is the case. But what is very important is that you can see on this slide, on the left part on this slide, that there is a gap between 1990 to 2000. In fact, there was a gap in the definition or in the construction of radar parametry. All the experiments start in the 70s, 80s, and then stop. And we stop to work on radar parametry, and we start again in the 1990s, in the 2000, because it was difficult due to a very simple device, only a component in the radar system. It is a switch device, so you will see later on what it means. It was very difficult at this time to develop a switch which was able to switch very fast and which was able to transmit a lot of power. So this is why we stopped to develop this kind of radar parametric system. And then in the 90s, we find a possibility to construct this device using a pin diode, and which give a good compromise in the switch and in the transmitted power. And then start again, the research in radar parametry. Okay, so now I'm going to present to you some different space-bound sensors and parametric space-bound sensor. But first of all, we are going to start with a non-parametric, space-bound SAR space-bound sensor. So as you may know, the first SAR system launch was a CSAT in 1978. It was not at all a parametric SAR system. It was a classical one-channel SAR system. I shall not come back to the history of this space-bound. It's a very nice story, but we have not the time. Then we have the first European system, ERS-1. The first Japanese system, GRS-1. Then the first Canadian system, RadarSat-1. The second European system, ERS-2. And something which is very important, a very experiment, it is a SRTM in 2000, which means a Shuttle Radar Tomography mission. It is thanks to this experiment that today we can use SRTM data to have an idea about the topography. So just to say to you that this very well-known SAR system are not at all parametric system. What does it mean? It means that the architecture is the following. You have just one transmitter and one receiver with one antenna. So what does it mean? You have seen yesterday during the presentation of TWI about the radar, the basics on SAR processing, that you transmit what we call chirps, this kind of radar signal, and we are going to receive using an antenna and using a receiver. But you can see that the antenna will be able to catch the information along one direction, which corresponds to the polarization of the antenna. So what does it mean? It means that if I'm going to use a horizontal antenna, I shall be able to measure only the horizontal component of the wave. So it means that I'm going to lose the vertical component of the wave. Remember what I have presented to you some slides before, the green components and the blue components. Okay, the green component is a horizontal component, the blue component is a vertical component. So if I have only one antenna, I shall be able to measure only one of these two components. Okay? So in such a case, it is not at all a parametric system because I have lost one information. So this is a classical backscattering coefficient system. So you have no parameter. For example, this is a SAR image of the well-known San Francisco area. So you have the ground truth on the right, and you have the SAR radar image in the HH component. What does it mean? It means that due to the fact that I'm going to use only one antenna, I'm going to transmit only one polarization, the horizontal polarization. I'm going to receive only the horizontal component. Okay, so I can create this image. Or, if I want, I can change my antenna, I can transmit a vertical polarization, but I shall measure only the vertical component. So in such a case, I can get this image. So what is very interesting is that if I go from one image to the second one, so you can see that the SAR image is changing. So it means that the environment is very sensitive to the polarization I'm going to use during the transmission. For example, if you have a look to the sea surface, you can see that the sea surface is more bright in the VV channel, so it means that the sea surface is more sensitive to the vertical polarization compared to the horizontal one. So it was just an example to show that somewhere polarization is very important because you can have a better discrimination between the different interactions. Okay, so to create a polarimetric system, what do we need? We need, in fact, to add a second receiver and a second antenna. Okay, so I will continue to transmit my wave using, for example, the horizontal antenna. But thanks to my two receivers, I shall be able now to measure the two components of the wave. So like that, I shall start to have an information about the polarimetry, the polarization of the wave, because I can measure the two components. So this is a starting point if I want to make some polarimetry. But it is not a fully polarimetric system. It's just a dual polarimetric system because I can measure only the two components. So HH and VH. So, for example, I come back to my San Francisco area, and you can see on this slide, on the left, you have the HH channel, and on the right, you have the HV channel. So what does it mean? It means that I transmit the horizontal polarization and I receive the vertical component. Well, in fact, I'm going to have the information where I have a total depolarization of the wave due to the different interaction which can occur inside each pixel. So you can see that I transmit horizontal, I receive vertical. So I have a total depolarization of the wave. But this is very complementary information, so this is very interesting, very interesting. So the most important spacebound system which was able to provide this kind of information, the first one was SAR on board of Hanvisat from ESA. Okay, so then we have, still today, it is a current system, we have a Cosmos SkyMed, which is a dual pole system, which is a constellation. And you can see that we have a revisit time of 1 day. So just to illustrate here, it was a SAR image of the catastrophe of the Costa Concordia some years ago. The Cosmos SkyMed is a dual pole system. Then you have TerraSAR X from DLR. It is in a Higgs band, very high frequency. And with the system, we can have what we call a twin configuration. It means that I can measure HH and VV. You can measure sometimes the cross polarization channel, HV, but only in experimental mode. And we have still today the Indian system, RISAT 1A, which was launched some years ago in C-band. So it is a dual pole system. It is also a hybrid pole system. So I shall not go into the details of this configuration, but it is also a very interesting configuration. It means that you are going to mix different kind of polarization during the transmission and during the reception. So this is what we call hybrid polarization, or what we can call also compact polarization. And we have the Sentinel-1A, which is a dual pole system, which provides HH-HV or VV-VH. Okay, so it was just to illustrate, as I presented to you at the beginning, my home city in Britain, in Rennes. Okay, so now, what can I change to move from a dual pole system to a fully parametric system? In the previous architecture I showed before, you have seen that I transmit the wave using the horizontal antenna, but I can do also using the vertical antenna. So I can transmit either with the horizontal antenna or with the vertical antenna. So the idea was to include here the switch, the famous switch. The switch which must switch very fast and which must be able to transmit a lot of power, because the transmitter is just before the antenna. Okay, so what does it mean? It means that I'm going to transmit a horizontal wave, I'm going to receive, then I'm going to switch, then I'm going to transmit a vertical wave, I'm going to receive, then I'm going to switch again to transmit horizontal, then to switch again to transmit vertical, etc., etc. So if I have such a system, it means that I can construct all the parametric information. So this is a fully parametric system. It means that in such a case, you can have access to the HH channel, HV channel, VH channel, and VV channel. Okay, you have all the information. And the output will be what we call the scattering matrix or the Sinclair matrix. So this is a fully parametric architecture radar system. And so like that, you can have access to these three images, HH, HV, and VV. So here you have all the information. So you can say to me, VH is missing. Yes, okay. But Maxwell told us that there is what we call the reciprocity theorem. It means that if I transmit horizontal and I receive vertical, it is exactly the same thing if I transmit vertical and if I receive horizontal. So this is why the reciprocity means that the HV equals VH. It is not true, but it is not false. It is true when you do measurements in a very nice environment like a anechoic chamber. So in such a case, HV equals VH, no problem. In our case, due to the change of the radar system and displacement of the radar system during the acquisition, you are not going to see exactly the environment in exactly the same configuration, because you move a little bit when you switch from horizontal to vertical. This is why HV is not at all equal to VH, but is very, 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 very close. Usually we admit that HV equals VH. Okay, so in conclusion, I have three images. HH, HV, and VV. So if I have three images, the natural reflex is to construct, for example, a false color image. False color image or color image, remember we have three channels, the blue, the green, the red. Okay? So I'm going to put the HH on the blue, the HV on the green, and the VV on the red. And this is this kind of image we can get. So this is what we call the fully Sinclair color image. Okay, so it is a false color, but it's nice. It means that I can immediately have maybe a first interpretation of the different scattering mechanism. So this image confirms what I explained to you before, that VV was very, or was most important for the sea surface analysis, because sea surface is more sensitive to the vertical position. And you can see here that the resulting color is very close to red. So it's very close to the VV information. Oh, okay, so it was the first step. It was the first time that we were able to construct this kind of image using this free channel. And some years later, with my colleague Sean Cloud, we were working on this different kind of combination between the different channels. And we have seen, we can demonstrate, it's not difficult to demonstrate, that if I had HH plus VV, I'm very sensitive to the single bounce scattering mechanism. Okay, single bounce, it means only one bounce, only one interaction between the wave and the environment. HH plus VV, single bounce. And when we subtract HH to VV, HH minus VV, in such a case, we are more sensitive to double bounce. Okay, so for imaging, I have a building, I have a parking, and so I can have a double bounce between the wave, between the building and the parking and coming back to the radar. Okay, so HH minus VV is more close to double bounce, and HH plus VV more close to single bounce. And you can see the result of this combination on these two images. You can see that HH minus VV is very low on the C surface. You have not a lot of double bounce on C surface. You have more single bounce on C surface, or you have more double bounce on the urban area compared to the single bounce, etc., etc. So the idea now was the following. I'm going to use the HH plus VV for the blue channel. I'm going to use the HH minus VV for the red channel, and I continue to use the HV for the green channel. And I get this very nice color combination. So this is what we call the Pauli color combination, because from a mathematical point of view, this combination, the result of the projection of the scattering matrix on the Pauli group of matrices. So this is why we call this the false color Pauli representation. And so this is very interesting, and usually this is what we do when we receive a fully parametric SAR image without any a priori information. The first step is to construct this kind of image, because immediately you can have a very basic, very simple, very light interpretation of the scattering mechanism which could occur inside each pixel.
Eric, we have two questions in the chat.
Yeah. Okay, I'm just
okay.
Discovering.
So one says, would you remind us again which sensor acquired these images over San Francisco?
Yeah, this is Hellos. And we shall use this image this afternoon for the practical. Okay, so this is a Hellos 1 SAR image of the area. Okay, so Hellos, it is a Japanese system.
Is it left looking?
I'm not going to give you the answer because it will be a question I shall ask this afternoon. Okay, during the practical. If it is a left looking, or if it is a right looking, if it is a ascending orbit, or if it is a descending orbit. Okay, so it will be a question of my practical this afternoon. So I'm not going to give you the answer now.
And there's another question by an observer, Tunyan Yang.
Question regarding bounce scattering. It's only representative of double bounce or the thing. Yes. Okay, you are perfectly right. I make a mistake when I say single bounce, or double bounce. No, I have to say even bounces or odd bounces. It's natural to say single bounce or double bounce, but you're right. It must be even bounces or odd bounces, because you can have three scattering mechanisms, three bounces, which are exactly identical to a single bounce, or you can have four different scattering mechanisms, four different bounces, which will be equivalent to double bounce. Yeah, you're right. Yeah, but usually we say single and doubles. Okay. A good illustration of this point for the three bounces is if you study the radar cross-section of a triedral. You know what is a triedral? It is a kind of a target we use for calibration of airborne sensor or spaceborne sensor. We use triedral for calibration instead of a plate due to the pattern of the triedral. The flat plate has a very thin pattern, so you must be exactly just in front of the plate to receive some scattering information. But with the triedral, the pattern is more open, so it's not necessary to be just in front of the triedral to receive information. So what is very important in the triedral is that you have three corners inside. So in fact, the wave will have three interactions before coming back to the radar. So if you study the radar cross-section of the triedral, this is an example of three bounces. And when you derive the equivalent scattering matrix, the scattering matrix is equivalent to a flat plate, so equivalent to a single bounce scattering matrix. So it is an example where the triedral and a flat plate have exactly the same scattering matrix. One presents single bounce, the second one presents three bounces. It is a way to demonstrate not HV. I said at the beginning, as you can see here, between HH and VV. Not HV. HV, you can see HV on this image in the image in the middle of the slide. You can see that HV is very dark. So it means that you have no depolarization. The C surface is a rough surface. Okay? So at the limit, it is a flat surface. If I have an horizontal wave, there is no reason why the wave is changing to a vertical component and coming back as a vertical polarization. So this is why there is no depolarization. This is why HV is very, very, very low on this surface. On this image, HV is very dark. Now, if I compare HH and VV, in fact, this is due to the reflection of a surface. This is due to the Fresnel coefficient. To the Fresnel reflection coefficient. And you can show with the Fresnel coefficient that the VV coefficient is higher than the HH coefficient. So this is why you have more scattering back in the VV configuration compared to the horizontal configuration. So this is why VV is more bright compared to HH. So the C surface, like a surface, is more sensitive to a vertical polarization compared to the horizontal polarization. Okay. Okay, so we can continue. Okay. So to illustrate what kind of sensor we have or we had. So the first fully parametric SAR sensor, in fact, was an experimental mission with a shuttle. It was a SAR and XR. SAR means shuttle imaging radar in C-band. So it was in 1994, it was the first time that we had a fully parametric SAR system in a spaceborne mission. And the first image was this one. It was an image in Africa, in Rwanda. Zaire and Uganda, the the border of the three countries. So it was the first experimental mission. And so like that, we said, okay, it works. So we can launch a fully polarimetric SAR system. Then we had the first one, which is Hellas 1. So this is this image we shall study this afternoon. So it was Hellas 1 in Hellbound in 2006. So it was on Pulsar. It was the name of the radar. Hellas is the name of the spaceborne. Then today we have still working RadarSat 2 from Canada in C-band. So you can see this is the same image of San Francisco area, but in C-band. So I shall come back on this image because you can play with these two images, and in such a case you can derive a multi-frequency approach. Okay, when your two images are perfectly overlap, you can have a Hellbound interpretation and a C-band interpretation. It is not at all the same frequency, so you will not observe exactly the same scattering mechanism. Then we have Hellas 2. We are working today with Hellas 2 because Hellas 1 is dead. So we are working with Hellas 2 from Japan, from JAXA, with a better resolution compared to Hellas 1. So we can have access to some fully polarimetric SAR image with Hellas 2. So here it is just to compare the resolution. So you can see on the right the same area with Hellas 2 with a higher spatial resolution compared to Hellas 1. And then we have the Chinese system. The name is Gaofen 3. So it was launched some years ago. It is in C-band, and it's very, very beautiful system which provides very high accuracy parametric information. And you can see here, for example, the internal wave of the ocean or inside the bay. So this is still San Francisco area. It's funny because during the time, this area is becoming what we call a super site. And so each time a new sensor is launched, by definition, 1 moment, you will get this San Francisco area measured, and you can have access to these images, and you can. It's a good way to compare the information between the different systems. Very interesting. Then recently we have the SAOCOM from Argentina, which is also a fully polarimetric SAR system. It is a dual pole, but also a quad pole system. And we have very recently also the new RadarSat system, what we call the RadarSat Constellation Mission, RCM, which is also a quad pole system, a fully polarimetric system. So this system is a very nice one because it can provide dual polarimetric, quad polarimetric, and also hybrid parametric information, compact polarization. So it's very nice. And we have also the new Cosmos SkyMed, what we call the second generation, which provide also dual pole and quad pole. And as you heard yesterday, we shall have the new biomass system, which will be a fully polarimetric system in P-band. So by definition, it must be a fully polarimetric system for the simple reason concerning the Faraday rotation, because the only way to compensate the Faraday rotation, you see that the Faraday rotation corresponds to a rotation of the electromagnetic field. So it means I'm going to change the polarization. So the only way to adjust or to correct the change of polarization is to apply a rotation operator, and to apply a rotation operator, we shall see that we need fully polarimetric information. So by definition, biomass system must be a fully polarimetric system. Okay, so we have also the NovaSAR in a S-band from England. It is a system working and providing this kind of information, not the phase, but the amplitude. That is a nice system. And in the next future, we shall have NISAR, you heard about it yesterday also, in L-band and S-band, a collaboration between a laser and a HISRO. And in the next future, we shall have the new generation of the Japanese system, which will be the HELOS-4 system with a higher resolution and increase footprint, a very, very important footprint. So we are all waiting after this new system. So to illustrate what I presented to you, if I take always my area, so this is what I introduced to you at the beginning during the introduction. So this is a fully parametric SAR image of my home city using the HELOS-1 system, the HELOS-2 system, the RadarSat-2 system, and Sentinel-1. And these 4 images correspond to a false color Pauli image. And the new one with the Chinese system, the GF3, also a Pauli representation. So the red colors correspond to double bonds in the center of the city. The green correspond to forest, to vegetation, and the blue correspond to fields, open fields. Okay, so it was a presentation of the different sensors. Now, if I want to process this data, we have a specific toolbox which is PulsarPro. Pro. So I shall present to you PulsarPro Pro this afternoon. So it is a very nice adventure, which started in 2003. So it is 18 years ago. So we start with PulsarPro Pro version 1, 2, 3, 4, 5, 6. Today we are on version 6. And this software is dedicated to the biomass mission. So I call this the development of this software, I call it an international collaborative project, because it is something which is very improving and upgrading weeks after weeks. So I receive a lot of contribution by a lot of people from different space agencies, university, research centers. And usually we work together, and if the routines or if the new signal processing code is very interesting, we can implement inside the software. So just an example, I was contacted 2 days ago by one of our colleagues from Canada, and he proposed to me to implement a new model-based decomposition. So he sent to me an example of the code. So I have not the time today to work on it, but I shall work on it next week. And if everything is correct, we shall implement this new code inside the software, and it will be available for the next release. So like that, all the international community can benefit of the development of this new functionalities. Okay, so we shall play with this software this afternoon. And I develop a dedicated web server, so where you can download the software. So the link is here, www.ietr, which is the name of my institute, and PulsarPro Bio, and you can contact us. We have a specific email address, pulsarpro.team@yahoo.com. And so you can send questions how to use the software. We have also a link, so I shall present to you this afternoon. We have also a link with a forum at the ISASTEP website, and we have also here some exchange about how to use the software. And I propose, this is very important, some fully parametric sample datasets if you want to start to learn with. So by definition, I have taken the San Francisco area, and so I propose the same area as I explained to you before. The same area which was acquired by a airborne system, SAR, and by the different space-borne system, LS1, LS2, Gauss, RadarSat 2, RISAT, Sentinel-1, Sentinel-1B, etc. So you can download all these images for free. You can use a Pulsar Pro to import this dataset, and then you can train using these images, and you can compare different resolution, different frequency, different observation configuration, etc., etc. Okay, and to conclude this introduction, I am an old professor at the university, so I like to train my students and to train the next PI generation, because you are the next. Okay, a greeting from Canada. Yes, here's my colleague Ashley Richardson, who proposed to be his new decomposition. Okay, so you are the next PI generation, so we have to train you. And we have published different books. Okay, so the first book, this one was published by Professor Borner some years ago, so it's a kind of a Bible. You can see the number of pages, quite 1,000 pages. It's very interesting because it is a very global overview of polarimetry. And I have taken some part of this book to include inside Pulsar Pro, so you can have access also to this kind of information. We published some years ago a book with Janssen about the basics concerning parametric radar imaging. We have also a book published by Shane Cloud, which is more focused on SAR Polarimetry plus interferometry. So it is very, very important book too, covering SAR application. And our two books were translated in Chinese by our colleague Professor Wan Hong and Dr. Tian Yin from the Institute of Electronics, the Chinese Academy of Science. So we have our two books in Chinese. And recently we have one book from Charlie Lachey and Jakob von Zyl from GPL, from NASA, very important. And another one from Harold Mott, who was also a father of radar, not only parametry, but of radar directly, Harold Mott. And we have a new book from Jakob von Zyl and Young-Sin Kim from GPL. And unfortunately, Jakob passed away. It's a real pity, passed away some months ago. And the last one, which was very, very published very recently by our colleagues from Japan, Yoshio Yamaguchi. And you will heard about him during the day concerning the different decomposition theorem, because he has proposed a lot of decomposition theorem, the Yamaguchi decomposition. And we have a very new book, which was published very recently. You can see it was last March. The name is Parametric Synthetic Aperture Radar: Principle and Application. So this book covered a lot of different topics, and we have a lot of contributors on this book, and you can download this book for free because it is a open literature. So the editor are Irena Hanchek from DLR, so you will see Irena on Thursday, and Yves Desnos from HISA, who is the head of the research department at HISA, H3. And I propose, I provide also this book inside the Pulsar Pro environment. So you will see this afternoon how you can have access to this book. Okay, so it was the end of the introduction. Okay, oops. Okay, so it was just details about about the new decomposition Dr. Richardson proposed to me. Okay, it was not his decomposition, yes. It was a decomposition which was published by Dr. Day, Professor Bhattacharya, Professor Freire, and Professor Martinez, etc., etc. Okay, the resolution of GF3 is, if I remember, is 8 meters. 8 meters. Okay? It's a good system, good resolution. Okay, so if you have no more questions, okay, so we are going to go into the details of the theory. And so to illustrate my presentation, I shall use, again, San Francisco area, but measured this time by the airborne system, SAR, from GPL. So in fact, it was the first fully polarimetric SAR image, Okay, so you can see on the right the false color poly image. So you can it is a airborne system, so with a very high resolution. So you can see all the details. It is not a picture, it is not a photo, it is a radar image, color-coded image with a polarization. And you can even detect or discriminate the trees along the two big boulevards on the city. You can see the red colors more or less in the urban areas, which correspond to the double bonds. You have the green colors in the parks, in the vegetation, which correspond to volume scattering mechanism or vegetation scattering mechanism. And you can see also some change of the roughness of the sea surface on the bay and on the surface. So we shall use this image to illustrate the different concepts I'm going to present to you. And this afternoon, during the practical, we shall use this image, so this area. So we shall use Pulsar Pro to process the image, and at the same time we shall use a snap to make the co-registration of the image. And so you can see here you have an overlay the fully polarimetric SAR image over Google Earth. So like that, you can see that there is a one-to-one corresponding. So it's very important to have a physical interpretation of the different scattering mechanism we can detect inside each pixel. Okay. So we can start with a basic concept about the definition of what is the polarization of electromagnetic wave and how we can slowly define the representation of the polarization. Okay, so as I said during one of my previous slides, Maxwell is our God because he was the first who was able to take all the different equations provided by Faraday, by Ampere, or by Gauss, which describe the different relation between the electric field, with the magnetic field, etc., to create what we call the Maxwell equations, which are here. Okay, so we have the Maxwell-Faraday equations, the Maxwell-Ampere equations, the Gauss theorem, and we have the magnetic field, we have the electric field, we have the parameters, the conductivity, permeability, and permittivity. So the idea with these equations is to be able to derive the equation which gives you the information on how an electromagnetic wave propagates at the output of the antenna, how the wave is going to propagate from the radar to the environment. If I play with all these equations, I get this propagation equation, which is in the middle here of the slide. then Helmholtz derived what we call the Helmholtz propagation equation, or what we call the telegraphist propagation equation. In fact, he starts from the previous equation and he makes some simplification because we are living today in a source south-free environment. You have not magnetic particles floating around you, so it is a source-free environment. It is a linear environment. It is a homogeneous environment. It is isotropic environment. It is dielectric and lossless medium. So this is the real equation of the propagation of the field. And then from this equation, instead of working in the time domain or in the space domain, we are going to work in the complex domain. Okay, I'm going to move to the complex from a mathematical point of view to the complex domain. It's just an artifact to simplify the writing of this equation. And here we are going to introduce, trying to put a kind of, okay, we are going, you see that? We are going to introduce a complex representation of the vector, of the field, and the name is what we call the Jones vector. And we come back, it's possible to come back to the space-time domain by taking the real part of this complex vector multiplied by the propagation frequency further. And so we can write this equation in a very simple way here in the complex domain. And we are trying to find the solution of this equation. And the solution of this equation is very obvious. It is what we call a sinusoidal plane wave. So what does it mean? It means that the wave propagates at the output of the antenna in a plane. Here you have a plane which propagates along the z-axis. And inside this plane, you have the field which is turning according to its polarization. So it's like that we are able to define the polarization of the wave. Okay, so to illustrate what I said, this is the output of the antenna. So the antenna is here. And the output of the antenna, you have two components, two sinusoidal components. In blue, the vertical component. In green, the horizontal component. And the combination of these two components create the red propagation of the electric field. So as you can see, it is described in a plane because I have only two components, the Y component, the X component, and you have no information along the Z component, along the propagation axis component. So this is a plane. It is a plane. And if I project this field in a plane, so imagine I take a picture, I'm able to take a picture. I look to the plane, and I shall see that inside the plane, the field is going to describe an ellipse. And this ellipse is what we call the polarization ellipse. So it is from the knowledge of this polarization ellipse that I shall be able to introduce some geometrical parameters which describe the polarization of the wave. Okay, and here you have the definition of the equation of this ellipse. In fact, it's very easy. You come back from the definition of the vector. You have just to substitute this feather between these two components. Okay, and you get the equation of this ellipse. Okay, so now if I look, to this plane and if I look to the ellipse. So this is in red, the ellipse, and I can describe this ellipse, this polarization, with some angles and with some geometrical parameters. So the first parameter is the length, which corresponds to the amplitude of the wave. The second parameter is the orientation of the ellipse. phi here. So this is the orientation of this long axis compared to the horizontal. And the second angle is what we call the ellipticity angle, which corresponds to the opening of the ellipse, the angle between the short axis and the long axis of the ellipse. Which one is the plane? Isn't it Z? Okay, the best explanation of this that I ever heard of this. So, okay. It's Y plus Z. Okay, so I come back. So, at the output of the antenna, I describe with my two axes, X and Y. And Z is the propagation axis. Okay? So I stop on the coordinate Z0. And the plane is defined always in the X, Y coordinates at the point Z0. Okay? So the plane is the X, Y plane. Okay. Which one is the plane? Z. No. The plane is not Z. The plane is defined at a position Z0 along the Z axis. Okay? Yes, the X-Y plane is moving. Okay. Can you show how the ellipse occlusion? Okay. Yeah, you see you have the horizontal components, Ex equals the magnitude of the sinusoidal components, omega t minus kz minus delta x, so this is the phase. And on the y component, you have exactly the same thing, except that it is another amplitude and it is another phase. So in common, you have in fact this what we call the phasor omega t minus kz. So what I have to do, I have to substitute during the derivation this phasor between these two equations. And you can see that as a result will be the ellipse, the polarization ellipse. And you can see that here you have no more the phasor. You have the components along the x-axis. You have the magnitude along the x-axis. You have the components along the y-axis, the magnitude along the y-axis. And you have delta, which is the difference between the phase. And you have no more the phasor omega t minus kz. Okay, so it is like that I can construct the ellipse equation. Okay? Yeah. You see, the electric field depends on space and time. So on this slide, you have everything at the same time. So imagine I take a picture, crack. Here, so I take a picture, I have no time, no more time effect. So here you can see on this red helicoidal the variation of the electric field along the z-axis. Now, so it is from one picture. I have no more time. I have only the z information. Now, if I look to the plane, in fact, I don't move. I am a position z0, but I'm looking what happened during the time. Okay, what happened during the time? So this is a variation of the field during the time. Okay, so the electric field depends on space and time. Somehow I cannot connect it. Yes, you can connect it. You can connect it because this field here depends on space and time, and here it depends on space and time. Okay. Yeah. So you have the direct connection of space and time at the same time. But if I want to separate what happened during the space or what happened during the time, so this is what I can do here. I take a picture, okay, no more time. I can see the field during the time, during the space. And if I go in a plane, here, I can see what happened during the time. So it is a space-time representation. And the polarization ellipse is defined, in fact, only once you have the complete description of the ellipse during the time. Okay? Okay, so if I continue to describe from a geometrical point of view, so I have introduced two angles, the orientation angle, phi, which is defined between minus 90 degrees and plus 90 degrees, and the ellipticity angle, tau, which is defined between 0 and 45 degrees. Okay, but if I put all the description, I shall have no more space to put everything. And you have to listen to just the name. You have the name here, phi equal, it is the orientation angle, tau, it is the ellipticity angle. Okay? A is the wave amplitude, and alpha is the absolute phase. So some point concerning alpha. Alpha is something that is impossible to measure. It is due to the physics. It is the position of the electric field at the output of the antenna. So just at the output of the antenna, as the position z equals 0, and time equals 0. Okay, so it is impossible to measure. So you have just to remember that each time we shall have a phase, which is a random phase. So it means that it will be very important to take care of this phase during different data processing, because it is a random phase. You have to do it more slowly later. Yeah, okay, no problem. I shall show you that from SAR you can download different information. You can download different book and publication, and you have all this part, which is described. Okay. Yeah. So to Peter and also to Conrad, from all the documentation I give, this is a difficult part. I agree with you. Don't worry, with my students, it is always the same thing. But it is just a first oral explanation. And after, when you read, usually it's more easy to understand, because you have already in mind some explanation. Okay, so I shall show you from SAR how to download the different information covering this topic. So you can read this after slowly, okay, and you will see. Okay, so if I continue to make my presentation here. So I describe the orientation of the ellipse, the ellipticity of the ellipse, and the last information is about the rotation sounds of the direction of the wave propagation. What does it mean? It means if the wave is turning right when it propagates, or if the wave is turning left when it propagates. So this is what we call the anti-clockwise rotation or the clockwise rotation, which corresponds to the left-handed polarization or which corresponds to the right-handed polarization. So we have a definition in the radar community, which is the following. I'm looking here at the antenna, and I'm looking into the direction of the wave propagation. Okay, so if the wave is turning along the clockwise rotation, it will be the right-handed polarization, and otherwise it will be the left-handed polarization. It is totally different from the optical community. Optical community is looking here to the wave arriving to the receiver and defining the polarization like that. In the radar community, up, we are looking on the other direction. It is not the same direction. So you understand immediately that we have a total disagreement with our colleagues from optics to define the sense of polarization. If I define a left-handed polarization, it will be a right-handed polarization from the optics. If I define right, it will be a left. So sometimes it's very difficult to interact with our colleagues from optics because we have a total different definition of the polarization. Well, anyway, it was just a story. So from a mathematical point of view, now it will be important to introduce somewhere the information of the sense of polarization. The solution is very easy. If I come back to the definition of my ellipticity angle, you can see that the definition of the ellipticity angle is not sine. It is like that between 0 and 45 degrees. Okay. So in such a case, I'm going to introduce a sine. If it is a left-handed polarization, the sign will be positive. And so in such a case, the ellipticity angle will be positive between 0 and 45. And if it is a right-handed polarization, I shall add a minus sign. And so the ellipticity angle will be between 0 and minus 45. Okay, so on this slide, we can summarize all what I have presented to you about the definition of the wave, about the definition of the polarization. So we start from the solution of the propagation equation, which is the following, which gives to us the information that it is a plane wave. I have no components along the z direction. It is a plane wave. And it is a sinusoidal plane wave because it is cosinus. So this is a representation in the time domain and space domain. From this representation, in fact, we prefer to use a complex representation. Remember, it was one of my first slides this morning. I said that we are going to deal with a complex vector representation of the polarization. This is the John vectors. It is a complex representation of the polarization. And it will be, in fact, the output of my antennas when I shall make some measurements. The output of my horizontal antenna will be this information. The output of my vertical antenna will be this information. So in fact, when you are going to receive a dual pole image on each pixel, you have a complex number. And this complex number is this information for one image and for the second image. Okay? This is directly what was measured by the antennas, by the radar system. And from this information, so you have the magnitude of the two components, and you have the phase of the two components. And according to what I have presented to you before, I can reconstruct the orientation of the ellipse, the ellipticity of the ellipse, and the absolute phase of this ellipse from this information, So to illustrate the correspondence, so we are going to start with a horizontal wave, which is described only by a horizontal vector. Then I'm going to, oops, if it's coming, okay. Then I'm going to apply a simple rotation along the z-axis, which is defined here. So in such a case, I shall have an oriented Jones vector. But my ellipse is still aligned. So the next rotation will be this one. So you can see that this second rotation introduces the opening of the ellipse. So introduce the ellipticity. And the last rotation introduce the position of the electric field at time equals 0 and z equals 0 using the last matrix. So to summarize what I said here, I just said that the information I have as the output of my two antennas, I can also write this information using the product of three matrices. And this is very important because these three matrices will be used later to introduce what we call an elliptical basis transformation. Okay, so to summarize, I'm going to summarize. This is the output here. This is the output of my two antennas. This is what I'm going to measure. This is the amplitude phase and the output of my two antennas. Okay, so it is a complex number, amplitude and phase. And according to what I have just introduced to you, from this information, I can reconstruct immediately the geometrical parameters. For example, the orientation of the ellipse will be given by this relation here, which is function of the magnitude of the two components, and which is function of the phase difference of the two components. Okay, so I measured this. I can construct this immediately. So I can construct immediately the orientation angle. I measured this. I can construct immediately the ellipticity. So it means I can measure the opening of the ellipse, if it is a line or if it is a circle. I measured this. I can construct immediately the amplitude of the wave. And I can construct immediately the absolute phase, which is a phase of one of the components. Okay, so this is a physical approach. This is an engineering approach, if you want. From the output of my antennas, I can reconstruct immediately the four geometrical parameters. And what is also very interesting is that from a mathematical point of view, I can also introduce a matrix representation of the same information, which is in fact the product of a three matrix, the three rotation matrix, which are in fact what we call the Pauli matrix. Okay, the name of this matrix is the Pauli matrix. So to illustrate these parts, we are going to take some examples. Imagine I have only a horizontal wave horizontal wave. So it means that the electric field will be along only the horizontal direction, along the x-axis. So the corresponding joint vector, the output of my two antennas, will be this vector. It means that I have an information along the x-axis. I have no information along the y-axis. Okay, so if I measure a horizontal wave, this is what I shall get, 1, 0. From this vector, if I reconstruct the geometrical parameters, so using the relation I have presented to you before, using this relation, this four relation, so I can see that the orientation angle is equal to 0. Okay, this is an horizontal wave, so orientation angle equal to 0. And the ellipticity equal to 0 because it is a horizontal polarization. It is a linear polarization. It is a line. So this is why the ellipse is closed. The ellipse is reduced to a line. Ellipticity equals 0. Now if I take the vertical polarization example, in fact I'm going to change horizontal by vertical. So the output of my two antennas will be the following. No information along the x-axis, information along the y-axis. If I derive the orientation angle, the rotation angle will be equal to 90 degrees. Here also the ellipticity will be equal to 0 because it is a linear polarization. And we can conclude by two important examples, which are the following. The circular polarization. Because you will learn that with the new system, the new configuration, what we call the hybrid polarization or the compact polarization, we are using circular polarization. So we have to define what is a circular polarization. And in fact, the circular polarization is given here. Okay. So we can say that we have exactly the same information on the x-axis and the y-axis. You can see that we have exactly the same magnitude. Chi is a complex number. What does it mean? It means that in fact, I have a phase difference of 90 degrees between the horizontal components and the vertical components. So you imagine you take two sinusoidal waves, you make a shift of 90 degrees of the vertical compared to the horizontal, and the combination of these two waves is going to create a perfect circular polarization. And this will be the output if I measure a left circular polarization. I shall get exactly the same magnitude as the output of my two antennas, but I shall have a phase difference of 90 degrees between the two measurements. If I want to derive the geometrical parameters, you can see that if I derive according to the previous relation the orientation angle, we can see that it is impossible to find a value of the orientation angle. This is logical by definition because it is a circle, and a circle has no orientation preference. Okay, so you have no orientation angle of a circle. So usually, by tradition, we are going to fix this angle to the 0 value. Okay, we consider that we have a 0 value. But what is very important is now the ellipticity angle. The ellipticity angle reaches its maximum value to 45 degrees. So the ellipse is totally open and becomes a circle. So at the beginning it is a line, and then I'm going to open the ellipse, and the ellipse becomes a circle, 45 degrees. And if I look to the sign, I find a plus 45 degrees, a sign positive, so it means it will be a left circular polarization. So the next one is a right circular polarization. Right circular polarization. In fact, you will measure exactly the same magnitude and between horizontal and vertical, exactly the same magnitude. What is changing is the phase. The phase difference between horizontal and vertical. In the first case, it was plus 90 degrees. In the second case, it will be minus 90 degrees. So one of the components will be delayed by 90 degrees phase compared to the first one. And so if I derive the geometrical parameters, I shall get exactly the same thing, except for the ellipticity. And here I shall get a minus sign, which corresponds to a right-handed circular polarization. Okay, so this is just some example to illustrate what we call the joint vectors. So what we shall get at the output of my antennas, what you will get inside the pixel when you are going to process a dual pole SAR image. Inside the pixel, you will have two complex values, which correspond to the joint vector. And from the previous relation I have presented to you, you will be able to reconstruct the geometrical parameters. So like that, you can have an idea about the polarization which is reflected by this kind of environment. So like that, you can analyze the sea surface, and you can see that if I transmit a given polarization, what will be the polarization back? So like that, using this relation, you can have the information about the polarization which is coming back to the radar. If it is a circular polarization, if it is a linear polarization, if it is a left-handed, a right-handed polarization, etc., etc. Okay, so if we continue, if I remember, we have a break in 5 minutes. Okay, so I have just the time to finish before the break, my first part. Oops. Okay. So the absolute value is 1. Yes. Okay, y1 over square root of 2. Okay. Because this is a unit vector. It means that the length of the vector must be equal to 1, unit vector. So it means that it is normalized. Vector. When you are going to calculate the amplitude of the circular, okay, I'm going to take this. Okay. So it will be 1 over square root of 2 square plus 1 over square root of 2 square. So it will be 1 over 2 plus 1 over 2 equal 1. Okay, so this is why you have 1 over square root in front here. Okay, to get the magnitude of the vector equal to 1. So the absolute value is 1, yes, because chi is equal to exponential chi p over 2. Okay, and a complex exponential, the magnitude is equal to 1. So how does the atmosphere affect the polarization? Okay, but the angle will be the same with no. Yeah, okay. I have two questions. So, okay, angles is angles, magnitude is magnitude. Okay. Angle will not change, so the rotation will be the same. The ellipticity will be the same, no problem. But it is the magnitude of the vector will change. Okay, so it is something which is completely different. The atmosphere affects the polarization. It is not the atmosphere, it is the ionosphere. It is another layer. Okay. So it is a Faraday rotation. So imagine you have a layer. Usually it is a plasma layer. So it means that you have a lot of free electrons inside this layer. The problem is that it is a random layer because you can get this effect now, and some seconds later this effect disappears, and some seconds later this effect comes again. So it's a very random effect. So imagine you have your SAR system at the top, and the SAR system is going to transmit an horizontal wave, a linear wave, like my finger. And when the wave is going to go through the ionosphere, due to the effect of the Faraday rotation, the field, in fact, is going to turn along the axis, along the propagation axis. The field is going to turn. So officially, you transmit an horizontal polarization, and concretely on the environment, maybe it will be a vertical polarization which is going to arrive to the environment. Okay, so the Faraday rotation is going to turn the polarization. So this is the effect. So the solution would be the following, and we have some Canadian colleagues working on that, will be to transmit a circular polarization. Because if I have a circular polarization, okay, if I have a rotation due to the Faraday rotation of the circular polarization, it is again a circular polarization. So the circular polarization is not affected by the Faraday rotation. Okay, this is a solution. But remember that this Faraday rotation, this problem due to the ionosphere, is only variable for low frequency. Okay. So in P-band, it will be the case. Using halos in L-band, it's not the case. Using TerraSAR X in X-band, it's not the case. Using an NovaSAR in S-band, it's not the case. In P-band, low frequency, it will be the case. Okay, so this is why I shall show you after how we can compensate, or it would be possible to compensate this rotation. Sorry if it is a dumb question. No, it's not a dumb question. It's never a dumb question. Are people still using? Yes, Bickel and Bates. Yeah, it is a way to estimate Faraday rotation. It is a good question. If I estimate the Faraday rotation pixel-wise or image-wise. What we did some years ago, we simulate. Sorry, we didn't simulate. Oops. We were using Hellos 1 image, and we were able to have an estimation of the Faraday rotation over all the image. In fact, we took all the pixels of the SAR image and we correct pixel per pixel, okay? But using a matrix, a correction matrix, which was estimated over all the image. Now, okay, so if I have if I have 5 minutes more, I would like just to finish this part just before the break, which is an important part, and which is coming from mathematics, and we can see how is magical mathematics. So we are going to create a polarization algebra. Okay, so I'm going to take my cup of mathematician. I'm going to create a world of polarimetry, a world of polarization. A world of polarization which contains a lot of vectors. Each vector is associated to a polarization state. I'm going to create some relation between these vectors. And the most important relation is the orthogonality between vectors. Okay, so you understand two orthogonal vectors. My two fingers are orthogonal. But what is important is that from that you can also define now some orthogonal polarization, because a polarization is associated to a vector is associated to orthogonality. So in conclusion, I can make two orthogonal polarization states. So this is what we are going to do now, how to construct this orthogonal polarization. And so the construction is very simple. We have seen that it is possible to write the output of my two antennas using the product of these three matrices. Okay, the three matrices: orientation, ellipticity, and absolute phase. And the starting point, if you remember, was the horizontal unit vector. Now, if I want to construct the orthogonal joint vectors, I'm going to keep exactly the same matrices. So I'm just going to change the unit vector. We start from the vertical unit vector. And so like that, I can construct the orthogonal joint vectors, which correspond to the orthogonal polarization. Okay? And so what I'm going to do, I'm going to develop everything. And if I want to compare two things, I need to have exactly the same reference. So I need to have the horizontal unit vector. So like that, I can compare these two orthogonal joint vectors. And if I compare, I shall get now these new matrices. And if I develop these two matrices, I can see if I compare, I can see that the orthogonal vector will have an orthogonal orientation of the ellipse, will have a symmetric angle of the ellipticity, and will have exactly the same absolute phase, or the opposite absolute phase, but it is a random value, so it's not a problem. So what does it mean? It means that if I have an horizontal vector with an orientation angle equal to 0, the orthogonal one will have an orientation equal to 90 degrees, horizontal, vertical. Okay. Now, if I have a left-handed circular polarization with an ellipticity equal plus 45 degrees, the orthogonal vector will have an ellipticity equal to minus 45. So it means that a right-handed circular polarization is orthogonal to left-handed polarization. So this is very important. So it is the last conclusion. And that if you consider a polarization state, the orthogonal polarization state will have an orientation angle plus 90 degrees and will have a change of polarization handness because the ellipticity will be equal to the minus ellipticity. Okay, so like that, left circular is orthogonal to right circular. So left and right correspond to a orthogonal polarization basis. This is a basis. So this is very important. It means that I can change my polarization basis without changing my antennas, but just from a signal processing point of view. Okay, so this is summarized in this relation. I'm starting from the horizontal vertical basis. So imaging, this is your two antennas. And I can change in my algebra, in my world of polarization, I can change the polarization without changing the antenna, but just applying this matrix transformation, and I can reconstruct a new basis. And so this is very important. So this is what we call an elliptical basis transformation. And we shall see after the break some examples to illustrate this basis transformation, and you will see what does it mean from a concrete point of view. Okay, so just to remember that using the Pauli matrices, okay, this is the Pauli matrices. This is a orthogonal group. This is what we call a special unitary transformation matrix. It is a specific group. So we shall use these matrices to make any kind of basis transformation. Okay, so this one, these three matrices, is a very, very important key point in polarimetry. So you have just to keep in mind that these matrices are not coming like that, but they are coming from the construction of the ellipse from a geometrical point of view. Okay, everything is related. And this is a classical elliptical basis transformation. Okay. And just to summarize of this slide, that in fact it was one of a German colleague, Ernst Lundberg, some years ago, in fact, some years, it is already 95, so 25 years ago. So he was the first who demonstrate all this transformation using this special unitary transformation matrix. Okay, so this is something we have to take care. Using this group of transformation. So now today we are clear about all the elliptical basis transformation. So thanks to Ernst Lundberg, we demonstrate everything from a mathematical point of view. Okay, so 25 years ago. Okay, so I think that we can make the break. Right. I have a question. I have a question before. Do the current mission all use circular? No. Terra X is using horizontal and vertical. Okay, horizontal and vertical. Okay. Trying to illustrate something. No, I can do it. It's difficult to run. So I'm trying to explain to you with my pen. Maybe have you seen some pictures of a radar system of satellite? It's very easy to create a horizontal antenna. It's very easy to create a vertical antenna because it is what we call active antennas. And behind some spots, you have an active circuit, what we call a patch. So you have a collection of a vertical patch and you have a collection of a horizontal patch. So this is very easy to create horizontal and vertical antenna. This is also quite easy to create a circular antenna because you need a horizontal plus a vertical. And just as the input of the antenna, you make a dephasor of 90 degrees of a vertical compared to a horizontal to create a circular polarization. So it's easy also. It's impossible to create an elliptical polarization antenna. Impossible. Because it's very sensitive from a hardware point of view. It's very difficult to create a pure orientation angle or to create a pure ellipticity angle from hardware point of view. So this is why we prefer to use horizontal and vertical. And from a mathematical approach, as I explained to you, with this matrix transformation, I can reconstruct an elliptical polarization just using signal processing. And I keep the hardware horizontal and vertical polarization because it's very easy to do such antenna. So on board, 95% of the antennas are horizontal and vertical polarization only. And so you receive always information in the horizontal and vertical basis. But with all the matrices I have presented to you, you can reconstruct, and we shall reconstruct after, all what you want using this basis transformation. With a new system, with RCM or RISAT also, they were able to integrate circular antenna polarization. So we know that today, RISAT is using circular, RCM is using circular, ALOS 2, maybe, we don't know, maybe. To do some hybrid polarizations, it means transmitting circular polarization. But remember that the most easy way to create an antenna is horizontal and vertical. And after you can do what you want with the linear processing. And the last question, what is the superscript in the wave propagation section? Is it time harmonic? Yes. G omega T, omega is a pulsation. Okay, omega equal 2 pi f, 2 pi frequency. Okay, so it is frequency, and t is time. It is a cosinus 2 pi ft. And from a complex writing, instead of writing cosinus function, I write the complex exponential function, exponential g omega t. Okay, no more questions?
Okay, Eric, so if you wish, we can go with the break.
Yeah.
Okay.
Yeah.